Globally, only 9% of plastics that we produce, which is over 340 million metric tons a year, actually gets recycled. The rest, 91%, ends up in landfills, incinerators, where it becomes carbon emissions and causes climate change, and it ends up in our oceans. Even plastics like this, which is a bale of relatively clean polyethylene, does not have markets. Especially in places like California, where we used to depend on exporting our plastics for over 60% of the materials. My name is Miranda Wang, and I'm the co-founder and CEO of BioCellection. We are recycling the unrecycled plastics. And we're doing this by creating new chemical recycling technology, and we're doing this with this team of 11 individuals with backgrounds in chemistry, chemical engineering, and material science. The plastics that we're targeting are called polyethylene. So a lot of you may not notice this, but in the everyday packaging materials we use, there's 6 common types of plastics that are used. And polyethylene makes up 2 of these, depending on the low density and the high density. So this is a material that makes up 1/3 of all the plastics out there, is the top plastic produced by quantity, yet is the one least talked about when we speak about innovations on recycling. The one we usually talk about is PET polyester, usually water bottles. So polyolefins, polyethylene, is actually a really big problem. And it's usually in the form of your Ziploc bags, your grocery bags, your agricultural plastics. Even though in places like California where we ban these shopping bags, we're actually seeing more and more of these. If you go tour places like Recology and Greenways, they're actually seeing more of this, especially with e-commerce packaging. You also have it in the high-density form with these containers, like shampoo containers and laundry detergent containers. And more packaging is being shifted into these polyethylenes. So we tackle these plastics, and what we do is we break them down. And so the thesis of what we're doing really came from the scientific discovery that plastics actually do break down in the environment. They naturally go through a process called oxidation, which means they slowly, on a chemical level, break down from a structure of hundreds of thousands of carbons down to smaller compounds with lots of oxygen groups. And usually this is done in a natural environment by bacteria or UV radiation, so it's uncontrolled and becomes microplastics. But the issue with these plastics is that they do break down, actually. That's what's causing the environmental problem out there. So what if we can control and accelerate the breakdown, the oxidation of these plastics, and stop it right at the time point where we can actually harvest useful chemicals from that? And that's exactly what we do. So we've created a process that's an oxidation-based depolymerization process. This picture here shows you captures from a time lapse of our 6-hour reaction. So what you start with is shredded reactor of 10 plastic bags, and after 6 hours you can see the plastics have not only melted, but they've actually chemically broken down into aqueous or liquid chemical compounds. And these chemical compounds that we create have between 4 to 18 carbons, and these are very valuable chemical building blocks. What we then do is, after breaking down the plastics, we actually harvest these chemicals and we purify them. And this was very difficult to develop and makes us very different from all the other chemical recycling technologies out there, which only focus on breaking down usually to oil, and then they try to give it to a refinery or somebody else who can use it who it's not compatible to use. But what we do is we actually bring it to purified virgin quality building blocks. And what we're doing now is we have actually created multiple materials, performance materials, using our own building blocks. So we've been able to demonstrate actually building back up, and not to the same plastics that we started with, which are very low value polyethylenes with poor economics, but we're now targeting the performance plastics that would go into building durable goods and that would have very high value to support this process scale up on free economics. So how our technology creates a circular economy from a linear economy is like this. We start with the linear plastics, the polyolefins. Right now, we're also beginning to test with polypropylenes. But from these chemical building blocks that we make, there are options to either turn them into biodegradable materials, for example, materials that would be used in diapers and sanitary napkins, to proteins and lipids through synthetic biology. Because these chemicals are actually so small and bioavailable that they can be used as a substrate or even energy source for these microbes. But the more interesting applications in the plastic space to create this circular economy is they can be turned into performance materials like nylons or polyurethanes or even photopolymers and be used in products that we all depend on every day. And what we would do is work with these brands and at the end of the life cycle of this product, take it back and recycle that material we made again so that we achieve a closed loop, but using the carbons that are actually originally starting from a linear life cycle. And so what we do is we work with waste management companies. We're in active pilot right now with the city of San Jose and Green Waste Recovery, which is the largest recycling company in South Bay. And they give us the polyethylenes from real city trash. So we're working with the trash from the apartments, from the single family homes, and they sort all the plastics. That's what they're really good at. They're a sorting facility. Once the plastics are sorted, they give us just the polyethylenes, and we break them down and then build back up. And we're targeting brands that would make consumer products where people like you all can actually be part of the solution by buying a product made from circular materials. And at the end of the life cycle of that product, it will come back to us again so that we will keep it in a closed loop. And I should mention one last thing. This is... Thank you. This is our model in the United States, where right now, where we are, landfill is really expensive. So we're financially sustainable through a business model where we charge a recycling service fee to cities and waste management plants to actually provide a recycling service for waste management companies, because right now this material is being landfilled at a national average of $50 a metric ton. So we get paid for a raw material. And we come over here and we sell our performance materials that are fully circular at the same market price as materials that companies like BASF sell. And the only way that these brands are able to get fully circular materials, because we control our entire process, is to work and adopt our new materials. But in countries like developing countries where they don't have established waste management systems and when we want to later go and make an impact, what we will do is change the model where we would create enough of our revenues from the sale of the downstream materials, and we would shift to actually pay trash pickers so that they can actually have the incentives to go pick up those plastics. So we're currently working on scaling up. This is an animation, it's a still, but this is a rendering of a system that we're creating for a chemical process. And we're based in Menlo Park, California, where we're currently actively working on scaling this up. And I'd be very excited to speak to any of you. And my co-founder, Jeannie, here is also in the audience. We have a table upstairs, and you can see some of the materials we've been making, our entire process. So feel free to come over. Thank you very much.